Hello and welcome. I'm Laurent Feuillet, and this is a pre-recorded video for this 2021. I will tell you about this paper, a brief announcement. The name is Local Certification of Graph Decompositions and Applications to Minor Free Classes. And this is joint work with Nicolas Bousquet and Théo Pierron, and the three of us are in Lyon. So in this paper, what we do is that we make progress on the following question. Does every graph class characterized by forbidden minors have a compact local certification? Okay, so this is probably very mysterious for most of you. So in this talk, I will basically explain what this question is. So I will first explain what local certification is, then explain what graph minors are, and at the end, I will briefly mention our results and techniques. So let's start with the following scenario. So you have a network, and the nodes of this network, they want to compute some structure X. X can be a matching, a spanner, a coloring, your favorite combinatorial structure. Now, this network is supposed to be a tree, okay? So the nodes of the network, they know a fast local algorithm to compute X, but it works only on trees, okay? The problem is that, well, maybe there might be faults, okay? So the network might not be a tree. And this is bad because if you run your algorithm tailored for trees on something that is not a tree, you might run into trouble. For example, it might not terminate. Now, what we would like to do is to be able to check locally that the network is indeed a tree before we run the algorithm. And we want to do it locally because we want this verification to be efficient. We do not want the verification to be very long compared to this fast local algorithm. Okay, so good. And well, we are not interested only in trees. We are interested in general in checking network properties. Or in other words, we are interested in checking locally whether the graph belongs to some given graph class C. So C could be, for example, planar graphs. Many algorithms have been designed for planar graphs. Okay, so this is a scenario. And the problem is that this is impossible. So we ask for too much, okay? So checking locally whether the network is a tree is impossible in the following sense. So let's take a look at this picture. Here, I've selected a node, this white node on the right, and I've drawn its neighborhood at some distance 3. And you see that in its neighborhood, it looks like a tree. Everything looks like a tree. So this node cannot imagine that it's not in a tree. Okay. And if there is a cycle, and here there is a cycle, and if it's long enough, then the nodes cannot check locally whether the network is a tree or not. Okay. They cannot detect this long cycle. Any node on the network will be locally happy saying, yeah, on my side, it looks like a tree. Okay. And what we would like to have is that in a network that does not belong to the class, that does not have the right property, we would like that at least one node says, no, stop, I raise an alarm, let's not do that. This is not a proper network. Okay, that's what we would like to have. And this impossibility result for local checking, it's not only for trees, it's for basically any graph class. So it's impossible to check planar graphs. It's impossible to check whatever, like most graph classes. So this is kind of sad news. And what is done to overcome this problem is to bring some more information to the nodes in the form of a labeling. Okay, so you will put labels on the nodes of a network to certify that indeed the network is in the right class, okay? So maybe it's an algorithm that came before and that has computed this labeling, okay? And this labeling, you can check it locally, okay? That's what you want, okay? So now you have the network and every node has a label and you want to check locally that this label certifies that globally you have the right property, okay? And I won't go into the definitions, but here is a bit more of a feeling of a definition. So what we want is a local verification algorithm. So it's an algorithm that looks at some constant distance and or even at distance 1 and looks at the labels in this neighborhood and say, okay, it looks good to me, or no, it doesn't look good, I raise an alarm, okay? And we have two conditions that we want. We want that for every graph that is in the class, so for example, for every tree, we want that there exists a labeling such that the algorithm accepts in every node. So every node is happy with at least one labeling of the graph, okay? And now if a graph is not in the class, so for example, it's not a tree, then for every labeling, so even if it's an adversary that puts the labels, the algorithm will reject in at least one node. So there will always be one node to say, no, the information I have is inconsistent. Okay, so this is a bit complicated maybe, so it's much easier to understand this on an example. So for example, for trees, what you can do to convince the node that they really live in tree is that you can choose one node to be the root, and you can give to every node its distance to the root, okay? So now what a node can do is to check the consistency of the distances. This node at distance 4, it says that it has a neighbor at distance 3 and two neighbors at distance 5. This looks good, this makes sense. But now if I were in a cycle, and for every labeling, so this is just one example, but for every labeling the same would hold, there will be one node around which the distances do not make sense. They are inconsistent. For example, here it's not possible that in a tree you have two nodes with distance 6. Okay, so this is the kind of labeling we are looking for. Okay, and here are some things that we know. So we know that for every class that you would consider, you have a certification that exists, a local certification. But this can use very large labels, like n square bit labels. These labels, they are called certificates. Okay, so that's bad because this is very large. You don't want to store n square bits in every node. But the good news is that for trees, you can do it in log n with these distances that I've just shown you. And even for planar graphs, you can still do it in log n. And even for bounded genus graphs that are still a generalization, you can do it in log n. And so this log n, that's what we call a compact certification. That's the efficient certification, okay? So the idea now is to generalize even more. Like, can we go beyond bounded genus graphs? And what these three classes have in common is that they are characterized by something, an object from graph theory, which is called forbidden minors. Okay. So now, if I go back to my question, the question was, does every graph class characterized by forbidden minors have a compact local certification? So what I'm saying is it true that I can generalize this log n bound to every graph class that is defined by forbidden minors and not only these special cases? Okay. So, okay, what is a graph minor? Let's first have an informal definition. So a large graph G, so that's, for example, the thing I have on the right here, has a small graph H, for example, the one on the left, as a minor if H is hidden in G. Okay, the small graph is hidden in the large graph. So here, if I give you this this graph K5, so if we click on 5 nodes on the left, it's not clear what I mean by hidden on the right graph, but here is a way to see it much clearer. So I can somehow make group of nodes and make paths, etc., such that I have this K5 that somehow appears. Okay, so that's the informal definition. Like if your K5 is hidden in the large graph. And now the formal definition is not much more complicated. It's just saying that G as H as a minor, if one can transform G, so the big graph, into H, the small graph, by removing vertices and edges. For example, the vertices that I have on the top left here, I can just remove them completely, and also the edges that are around, and I can do edge contraction. So for example, here on my kind of blobs, on my kind of little sets, I can just contract them into just one node, and for every path that I have that links to this kind of blobs, I can just contract to have just one edge. And you see that at the end, what I will get is this K5, this H that I was looking for. Okay, so this graph, this big graph, it has H as a minor. Okay. Now what I am interested in is the graphs that do not have H as a minor. Okay, you give me a graph H, and now I consider the graphs that do not have H as a minor. Okay, so that's maybe a bit strange, but here is a simple example. The trees, they are exactly the graphs that do not have the triangle as a minor. So the triangle is this click on 3 node, K3, and here you can see on the picture how I can get a triangle minor in a graph that is not a tree. So I can just take a cycle, there is a cycle if it's not a tree, and now I can like choose some parts of the cycle to be what I will contract into nodes. Okay, so 3 such parts, and then I can just have paths that link these 3 blobs. Okay, and if I contract and if I remove everything else, etc., I will find this triangle. So this means that this graph is not triangle minor free, and well, you actually have this if and only if. Okay, trees are exactly the graphs that are triangle minor free. And well, there is a remarkable theorem that says that planar graphs are exactly the ones that do not have nor K5, neither K33 as minors. Okay. And then for graphs that have some genus, so that can be embedded on some surfaces, etc., there is also a list of forbidden minors. And this minor thing, it's really something that is super important in graph theory. It's not something I made up. It's something very deep on which there are very deep theorems. So it's something we want to understand from the point of view of local certification. Okay, so now I hope that everything is clear in this definition, in this question, sorry. So we are interested in this question: does every graph class characterized by forbidden minors have a compact local certification? So can we generalize what we have for trees, planar graph, bounded genus to this general thing where you just give me some graph or some list of small graphs and it generates a class, and I want to know if I can certify that this class is indeed what it is, if the graphs belong to this class. Okay, and what we do in this paper is that we give a partial answer. So what we say is that the answer is yes, if your minor is small enough. Okay, so what does small enough means? It means that this H that you are forbidding, it has less than 4 nodes, 4 or less, or it has maybe 5 nodes but with some special structure. So basically we say, okay, if the minor is small, then yes, indeed you can certify it with very small labels. But if the minor is larger, we don't know. Okay, so the question is still wide open. And what is more important maybe than just this answer is the tools we use. Okay, so what we do is that we certify some connectivity decomposition. So if you look at this picture, this is a decomposition based on 2 connectivity. Okay, I have done what is called a block cut tree. So each of this blue set, the blue part of the plane, it's a 2 connected component, and you see that if I have a graph, I can organize its 2 connected components into a tree, and there are these articulation points, these white vertices, okay, that are like articulating between the 2 connected components. And what we can do is to certify this decomposition. We can say to every node, okay, you are in this part of the decomposition, etc. And why is this useful? Because once you know that you are in a 2 connected component, then the structure of the H-3 graphs, they are more constrained, and then it's easier to certify this. So you can just certify, once you have the decomposition, you can certify one blue part, and then another blue part, and then another blue part, and all these certifications are easier than the certification of the whole graph, okay? But now, okay, there is a problem, which is that for these articulation points, these white vertices, we give them labels that correspond to, well, these 2 connected components and this other 2 connected component to which it also belongs, and maybe there are like an unbounded number of such components, so the certificates can grow very large, and we don't want that. We want short certificates, log-in certificates. So we also have to build some tools to avoid this phenomenon that we call certificate congestion. So these are our 2 main tools to get this partial answer. Well, that's all for this brief announcement talk. See you at DISC if you're there. And well, everything I've said and the paper is on archive with all the references to what I've said. And that's it. Thank you very much for watching.